Hello everyone. Our topic for the session is structure and preparation of alcohols and phenols. We can see the diagram over here of methanol, phenol and methoxymethane structures. There are certain points to specify and discuss over here. Like methanol is an example of alcohol. Phenol is an example of the entire aromatic system having OH linkage. Methoxymethane is an example of ether. So alcohol, phenol and ether. In case of this alcohol, methanol, the carbon atom is sp3 hybridized and the carbon atom of phenol is sp2 hybridized and carbon atom in case of ether is again sp3 hybridized. So, since the sp3 hybridization exists in the carbon atom of methanol, or I'll say alcohols, the expected bond angle is 109 degree 28 minutes. But the angle that we are seeing is 108.9 degree, which is lesser than that of 109 degree 28 minutes. This is due to the fact that the oxygen is having two lone pairs. These two unshared electron pairs or the lone pairs, they exert repulsion amongst them. And as per the VSEPR concept, we know that the lone pair repulsion is maximum. It is greater than a lone pair bond pair repulsion and even greater than a bond pair repulsion. This is it. So that's just the recapitulation of class 11 VSEPR, saying that lone pair repulsion is greater than a lone pair bond pair repulsion is greater than a bond pair repulsion. What we can see here is a lone pair repulsion in methanol, on account of which the bond angle has decreased. Over here we can see the bond angle in case of phenol. We can see it is 109 degree. 109 degree. Here we can see there is repulsion between repulsion between this phenyl ring and the lone pairs, because phenyl ring is also bulky in nature. On account of this repulsion, the bond angle is 109 degree. But yes, there is lone pair repulsion taking place here. In case of ethers, the bond angle, which was expected to be 109 degree 28 minutes, it's greater than that, and it is 111.7 degree. So this is greater than 109 degree 28 minutes. Why? It is due to the presence of two alkyl groups here. On account of lone pair repulsion, this bond comes closer. The angle tends to get reduced. But as it comes closer, on account of the presence of two alkyl group, again there is considerable repulsion. Due to that, after the bond angle decreases, there is a sudden or subtle increase resulting in an optical. Now in the same diagram, we need to see certain things. See, in case of methanol, the carbon-oxygen bond length is 142 picometer. In case of phenol, means in phenol, we can see the carbon-oxygen bond length is 136 picometer, which is less than that of 142 picometer. And in ethers, the carbon-oxygen bond length is near about 142. It's close to that 141. Now the question arises, in case of phenols, why the bond length is lesser and the difference is so much? Now the reason is the lone pair above oxygen in phenol that goes into resonance, we can see it is a plus R effect, for which the carbon oxygen bond, this bond, acquires a partial double bond character and the bond length shortens. Another point is that this carbon is sp2 hybridized, greater electronegativity, and bringing the shared pair of electron closer to it, trying to bring, for which the bond length decreases. But a more, I will say, apt reason will be stating about the resonance, stating about the partial double bond character. Now, preparation of alcohols, the first preparation is from alkenes. The method is acid catalyzed hydration. The term hydration is actually addition of H2O. It's addition of H2O, of course, in H and OH manner. Now, alkenes, when I'm talking about, it means C double bonded C system. This C double bonded C system may be symmetrical as well as unsymmetrical. If I assume that it is symmetrical alkene, addition of H2O in presence of H plus can lead to addition of H and OH in any manner. That means it can be like this, H and OH, and I can say this carbon is holding the H and the other carbon, it was unsaturated and now it has become saturated. The other carbon is holding the OH. But the question arises, what if an unsymmetrical alkene is taken? Suppose I have taken a propene system, CH3, CH, double bonded CH2. To this propene system, I am adding water in presence of acid as catalyst. So it is acid catalyzed hydration, addition of water. Now in this case, it follows Markovnikov's addition of HOH, where H, or rather I'll say OH, which is the negative part, gets added to the carbon atom having lesser number of hydrogen atom, and out of this two we can see this carbon is having lesser number of hydrogen. It's having only one. So OH gets added to this carbon and H gets added here, and the product that we will get as major product is CH3, CHOH and a CH3. So propan 2-ol or 2-propanol, this is your major product, and the minor product is CH3, CH2, CH2OH. This will be your minor product. So we should always remember that the hydration process is acid catalyzed. In presence of acid it takes place. We should remember that it follows Markovnikov's way of addition, and in order, just because it follows Markovnikov's way of addition, my major product will be. Now let's see the mechanism of acid catalyzed hydration. The step 1 involves protonation and generation of carbocation. Wherever there is generation of carbocation, we should be careful. That step is your slow RDS. So step 1 is your slow RDS. And here what is happening is, let us see it minutely. The lone pair above oxygen abstracts the proton and it forms H3O plus. The lone pair above oxygen abstracts the proton, forms H3O plus. This H3O plus, it acts as an electrophile. We know that electrophile is anything which is positively charged. So it is electrophilic addition reaction. That's why here it is given by electrophilic attack of H3O plus. So your step 1 is actually divided into 2 steps, A and B. The first step is generation of the electrophile, that is E plus. And that happens due to the presence of H2O and the lone pair above oxygen abstracting H plus. Now, electrophile is generated but it needs an electron excess center which is present in C double bonded C system. This is your electron excess center. Moreover, always keep in mind that whenever an electronegative atom gets a positive charge, it tries to get rid of that. So the pi cloud above these two carbon abstracts the proton and abstracts H plus from here, and it makes oxygen neutral like this. It makes oxygen neutral. Oxygen was having a positive charge, it gets rid of that, and you can obtain H2O, a neutral water molecule, which is a good leaving group. Now C double bonded C system, the pi cloud abstracts H plus. So this H plus gets attached to one of the carbon and the other carbon gets a positive charge. And so this is your carbocation intermediate. Again, I will say rate of the reaction will depend on the carbocation stability. So the major product that we got via Markovnikov mechanism, that was also due to the carbocation stability. So the stability of carbocation is again 3 degree greater than 2 degree greater than 1 degree, we all know. Step 2 is nucleophilic attack. It is nucleophilic attack. See, water H2O, oxygen having lone pair, it acts as a nucleophile. So H2O over here is acting like a nucleophile because oxygen is having a lone pair. And since you have got a positive center because of the formation of the carbocation, the lone pair above oxygen can attack the positive center and itself becoming again a positive charge. Now the carbon which was a positive center is no more positive. This is the positive charge is not there. See over here, the positive charge is not there. But oxygen has used its lone pair for the attack, so oxygen gets a positive charge over here. Again, the driving force is electronegative atom gets a positive charge and wants to get rid of that. So your step 3, here the step 3 is deprotonation. Always remember, apart from the slow RDS, all other steps are fast steps. So this is a fast step and this also is a fast step. But the rate of the reaction will always depend on slow RDS. So deprotonation means removal of proton. Now H2O has amphoteric nature, for which it can abstract the H plus. So oxygen uses its lone pair to abstract the H plus. It takes the H plus and simultaneously this bond opens up and neutralizes the charge over oxygen which was having positive charge. So H2O after taking H plus becomes H3O plus. So you can see the electrophile is regenerated. So for this reaction, catalytic amount of the reagent or H2O is required. That means very less quantity of H plus, very less quantity of the reagents can actually drive the reaction forward because it provides H3O plus in course of the reaction. So for this reason, we can just go back to this one where we were seeing that a propene system was having propan 2-ol as the major product. Probably because the carbocation that was obtained in position 2 was a more stable carbocation. It was 2 degree and so it gives the major product. And the carbocation that was obtained from this carbon was 1 degree, which gives you the minor product. The next method of preparation of alcohol from alkenes is by the method of hydroboration oxidation. This is an example of an alkene propene. Now, if I undergo hydration, acid catalyzed hydration, OH will be coming at carbon number 2. For acid catalyzed hydration, OH will be coming at carbon number 2. But when I carry out hydroboration oxidation, the OH in the final product, just see it is coming in carbon number 1. It looks like anti-Markovnikov manner of addition of HOH. Like OH is getting added to the carbon which is more, having more number of hydrogen atom, or which is less substituted, not more substituted. So it looks like anti-Markovnikov addition of HOH. But the point over here is the yield of propan 1-ol is quite good. So in the first step, what is happening is diborane is getting added in this manner. The carbon atom which is having more number of hydrogen atom here, their BH2 is getting added. On the other side, H is getting added. Now, if we consider this, like this is 1 unit of R. So we have got RBH2. We have considered the alkyl chain as R, and then we are writing RBH2. By the addition of another mole of R, we are getting R2BH by substituting 1H from BH2. So we are getting CH3, CH2, CH2 whole twice BH. Now again I am left with another H that can be substituted by another mole of the alkene. So here I get R3B by substituting the H, which is the trialkyl borane, which is the addition product. This is your trialkyl borane. Now this trialkyl borane is oxidized to alcohol by hydrogen peroxide in presence of aqueous sodium hydroxide. That's why H2O is written here, aqueous sodium hydroxide, OH minus is written here. So what happens is, you have to consider it in this manner that the bond breaks here, R and B breaks here. You get OH added here and BOH whole thrice as the side product. So it looks like this, that there has been anti-Markovnikov manner of addition of HOH. So if anyone wants to write the reaction in one step, combining the steps, the two steps, hydroboration and oxidation, it can be written in this manner. CH3CH double bonded CH2, I can sum up in this manner. Number 1, I can give BH3 whole twice diborane. So hydroboration will take place, the formation of R3B here. The formation of R3B will take place in this step. And the final step will be oxidation in presence of H2O2. So 3 moles of H2O2 and aqueous NaOH. So H2O, or you can say OH minus and H2O. This can be written. So in this case, we have to remember it takes place in anti-Markovnikov manner. It is anti-Markovnikov addition of HOH. So the negative part gets attached here where the number of hydrogen atom is more, because it is anti-manner. And H gets added here. So what will be my major product now? It will be propanol, CH3, CH2, CH2OH. So this is my major product. The side product is BOH whole thrice. Next, we can obtain alcohols from carbonyl compounds. What are carbonyl compounds? Carbonyl compounds are the compounds having this type of linkages. So basically carbonyls are aldehydes and ketones. They are collectively known as carbonyl compounds. Aldehydes have one H attached to C double bonded O. This is aldehyde linkage. And ketones doesn't have any H attached. This is ketone linkage. Both the side of C double bonded O are carbon atoms attached. So always remember that aldehydes, say RCHO, they get reduced. Reduction means addition of hydrogen, I can say, in presence of metals like nickel, platinum, or palladium to produce 1 degree alcohol. And it can be written as RCH2OH if you really want to show the linkage. So it is 1 degree alcohol that is obtained from the reduction or by the reduction of aldehydes. Now aldehydes give 1 degree alcohol. You can see by the I will say by reduction method, and this is known as catalytic hydrogenation. This method from aldehyde and ketone by reduction. So here I am mentioning that the method is reduction, and this reduction method is also known as catalytic hydrogenation. Catalytic hydrogenation, because it's a reaction with hydrogen in presence of catalyst. Okay, so by the method of catalytic hydrogenation you are obtaining this. Remember that for ketones I can mention R, C double bonded O, R or R dash. They are ketone. This is an example of aldehyde and this is an example of ketone. So ketones also undergo catalytic hydrogenation H2 in presence of nickel, platinum, palladium to give you 2 degree alcohol, and it can be written RCHOH, R or R dash. This is a 2 degree alcohol. Now the reducing agents can be sodium borohydride, better reducing agent. For ketones, it can be sodium borohydride. It is not that aldehydes cannot be reduced. It is difficult to reduce ketones. Aldehydes can be reduced using this very easily. For ketones, preference will be for better reducing agent, that is sodium borohydride or lithium aluminium hydride. LAH is also written. So I will suggest better use NaBH4, better use LiAlH4 for reduction of ketones. This is a better choice, for the reduction. So when you use this, aldehydes, what I said, aldehydes will yield primary alcohol, ketones will yield secondary alcohol. Now, the next thing that we need to discuss is by reduction of carboxylic acid and ester. By reduction of carboxylic acid, reduction method only of carboxylic acid. Carboxylic acid linkage is COOH linkage and esters. So this is your carboxyl linkage and the acid is carboxylic acid. Let us see. RC double bonded OOH is an example of carboxylic acid. Now they are reduced to primary alcohols in good yields by good reducing agents, and the reducing agent can be lithium aluminium hydride LiAlH4, which is a very strong reducing agent, followed by hydrolysis H2O, and you will get RCH2OH. This carbon atom is a 1 degree alcohol, we can see. So this is how you can obtain 1 degree alcohol, primary alcohol, by the reduction of carboxylic acid. Now lithium aluminium hydride, this reducing agent is a very strong reducing agent, but it's very expensive also. That's the problem. It's very expensive reagent. Therefore, when you are carrying out this on a large scale basis or for a large scale purpose, lithium aluminium hydride is not a good choice for commercial purposes. Commercially, what is being done is the acids are reduced, RCOOH. This is commercial purpose. So commercially, the acids are reduced to alcohol. Okay, acids are reduced to alcohol by converting them to ester, followed by reduction. So let us see how it is being done. For this, some alcohol is used, R-OH, some other alcohol is getting used in presence of acid, and you get ester. And this is an example of esterification reaction. This is an example of esterification reaction. We can see this is esterification. Acid and alcohol gives ester, and this reaction is known as esterification. So you have obtained an ester here. This is an ester, and this ester is subjected to H2 in presence of a catalyst. This catalyst can be PT, it can be PD, or it can be nickel also. So the ester is undergoing reduction. Reduction of ester is being done. For this, we are not needing the expensive reagent lithium aluminium hydride. So I can convert it to RCH2OH. This is 1 degree alcohol, and I can get R-OH back. So it is very much used and favored commercially, because see, I am using R-OH, I am getting back R-OH. So very little amount of R-OH can carry out the reaction. Moreover, I need not use a lithium aluminium hydride, which is an expensive reagent. So this is how we can obtain alcohols from carbonyls. This is the screen which I am actually showing you the entire thing together. The entire thing is this. So the first one you have seen from aldehyde, getting 1 degree alcohol by reduction. Reduction of ketone gives me 2 degree alcohol. Reduction of carboxylic acid gives me 1 degree alcohol. Using good reducing agent. Why good reducing agent? Why strong reducing agent? Lithium aluminium hydride. The reason is, if I don't use a strong reducing agent, I will get aldehyde and not 1 degree alcohol. So I need a strong reducing agent to get 1 degree alcohol. Now this using lithium aluminium hydride becomes quite expensive, for which an alternative method is chosen commercially through the formation of ester and then finally reduction of the ester in order to obtain the desired 1 degree alcohol. Now to sum up the concept, we need it in the next unit. So let us see. Aldehydes undergo reduction to 1 degree alcohol. Ketones undergo reduction to 2 degree alcohol. And carboxylic acids undergo reduction stepwise to aldehyde, which can again undergo reduction to 1 degree alcohol. Now, if I can use a strong reducing agent, then in that case, I can easily get 1 degree alcohol from carboxylic acid directly, and such a strong reducing agent can be lithium aluminium hydride. So this is the summation of what we have seen just now. Commercially, the use of lithium aluminium hydride is very expensive, for which the esterification step is followed. Commercially, the esterification and reduction step is followed. This is another method which is very, very important for all other units as well. From Grignard reagent. What is Grignard reagent? Grignard reagent we have seen in the previous unit also. It is RMgX, where there is a carbon to magnesium bond, where magnesium end develops a delta positive and carbon end develops a delta negative. Now Grignard reacts with carbonyls, or rather it is an addition reaction. It's an example of addition reaction over carbonyl compounds, C double bonded O linkage. So this C double bonded O linkage can be aldehydes as well as ketone. So remember that the addition reaction takes place in this manner. Carbonyl linkage, C double bonded O linkage, is a polar linkage because oxygen is delta negative and carbon is delta positive. There is a pi bond and there develops a polarity towards oxygen. Now Grignard reagent RMgX in this in this bond, carbon magnesium bond, there again polarity develops because of the electronegativity difference. So magnesium end gets a delta positive and alkyl end, carbon end, gets a delta negative. So what happens? This end acts as nucleophilic end and it attacks over the positive carbon center, opening up the bond, the pi bond between carbon and oxygen. And now I can see what is happening, that the carbonyl linkage forms an addition product or adduct where this R gets attached to the carbon and oxygen opens up as O minus holding the delta positive MgX. So oxygen holds MgX and this is the adduct. This is the adduct or the addition product, the intermediate. Now this undergoes hydrolysis. So I will write HOH or I can say H2O. It undergoes hydrolysis because again this oxygen and carbon bond, that's a polar linkage and the bond breaks here. The carbon end, this is the delta negative, this is the delta positive end. So carbon end holds OH and delta negative end holds H, and now I get like this. It is like this. R gets added up here. OH got attached plus MgOHX. This is what is happening. So carbonyls, they give alcohols with Grignard reagent. Now, what type of carbonyls? Aldehydes and ketones. Aldehyde, the simplest example of aldehyde is formaldehyde. HC double bonded OH. HCHO is formaldehyde. When this reacts with Grignard reagent RMgX, due to the difference in the polarity, here delta negative, here delta positive, Grignard magnesium delta positive and R delta negative, this R will attack the carbonyl carbon and oxygen will open up. This we have seen in the general mechanism. So we will get HCH, R gets attached to carbon and oxygen opens up and holds MgX. So OMgX I will see. This is your intermediate, it's an adduct. And the next step will be HOH, where the carbon oxygen bond will break and you will get OH added here and H added here because oxygen end is delta negative, carbon end is delta positive now. So you will get H, C, H, R and a OH here plus MgOHX. Now seeing the alcohol, you can see it is having only one alkyl group. So it is actually RCH2OH. So this alcohol is 1 degree alcohol. So I can sum up and I can say generally that HCHO, formaldehyde, reacts with RMgX followed by hydrolysis, HOH, to give 1 degree alcohol, or I can write RCH2OH, where this carbon is 1 degree. So with formaldehyde, I will get 1 degree alcohol. Other than formaldehyde, all other aldehydes, for that I can write C double bonded OH. The same thing will happen if I give R MgX, magnesium N delta positive, R will be delta negative. This will be attacking here. O will be opening up. Same method like before. I will get R, C, H, O opens up and holds MgX. R gets attached here. This is your adduct. The next step will be hydrolysis. The carbon-oxygen bond will break, or rather, here we can see one thing over here I will mark, that ये oxygen magnesium bond, here again a polarity is there. So the magnesium end, delta positive end, and here delta negative end. This way also you can see magnesium holding OH and oxygen holding H. Here again a polarity is there, because there is electronegativity, huge electronegativity difference between magnesium, which is very electropositive, and oxygen, which is very electronegative. So other than focusing on the carbon oxygen, I'll suggest focus on the oxygen magnesium bond, and the bond breaks up here. So when we see, our suggestion also changes, seeing it stepwise. So that's why I'm telling focus on oxygen and magnesium bond. So you will get here this oxygen having H, right? See, oxygen having H. So here I will say it is OH plus magnesium taking OH becomes MgOHX. The same thing. So this is again carbon having 2R. It's a 2 degree. It's a 2 degree alcohol. Now again, let me generalize it and let me sum up. Like we have seen in HOH, same thing I will HCHO, same thing I will say for RCHO. Aldehydes other than formaldehyde, all other aldehydes. It reacts with Grignard reagent RMgX followed by hydrolysis to give 2 degree ROH. So we can say we get what? 2 degree ROH, or we will get RCH R dash OH. This is again 2 degree. So using formaldehyde, we will get 1 degree alcohol. Using aldehyde other than formaldehyde, we will get 2 degree alcohol. This point is very, very important to note. The next point which we will do is with ketone. A and B was from aldehyde. This, see, this two, A and B was from aldehyde. One was formaldehyde and other one was other than formaldehyde, all other aldehydes. Now we will discuss about ketones. So from formaldehyde, I think you have understood what it is. From formaldehyde, we have got 1 degree alcohol. From other aldehydes, we have got 2 degree alcohol. So using a ketone, what can we get? Yes, you are correct. I think you have guessed it correctly. It is 3 degree alcohol. So a ketone is R, C double bonded O, R or R dash, I'm keeping it R, plus R dash NGX, just to keep the difference between R and R dash, such that you don't get confused. Again, I will say focus on this. This is a delta positive, this is delta negative, this is delta negative, this is delta positive. So R dash will attack, just bear with this once. R dash will attack the carbon and oxygen opens up. Because R dash is the nucleophilic end, it attacks the electrophilic site. Now we will get R, C, R was there, oxygen opens up, negative end, so holds MgX. So OMgX, carbon gets bonded to R dash. This is your addition product or adduct. After this, HOH or H2O also you can write. Again, in the previous one I said it's better to focus on oxygen and magnesium bond. Here there is huge electronegativity difference. Delta positive, delta negative. Delta negative holds H, delta positive holds OH. So now I will say R, C, R, Here is one R dash and this is OH. So the carbon atom has 1, 2, 3 alkyl group and so it is 3-degree alcohol, followed by formation of MgOHX as the side product. So let us summarize it. Aldehyde HCHO with Grignard RMGX followed by HOH hydrolysis gives 1-degree alcohol. Other aldehydes RCHO, the same thing, will give me 2-degree alcohol. I have written do means the previous reagent I have repeated. Now R, C double bonded O, R or R dash reacting with Grignard will give you 3-degree alcohol. This is the summary of the entire steps which you have seen. This completes the preparation of alcohol part. The next part that we have is the preparation of the phenol part. Please note that all my video has the board work given. So for that reason, please follow the description part nicely to get access to the board work as well. So moving on to preparation of phenols. 1 or 2 concepts I think in the previous unit we have seen. So let us recall. First preparation is from haloarenes because our previous unit was haloarenes. So in the chemical reactions of haloarenes we have seen this part. From haloarenes. So there was a reaction which is known as Dow's process. I hope all of you remember if you have followed my previous videos on the previous unit. So there it was chlorobenzene as the starting compound. This is chlorobenzene undergoing nucleophilic substitution under drastic condition. So number 1 was aqueous NaOH at 623 Kelvin and 300 atmospheric pressure. And let me tell you one thing, that if I am writing it stepwise, then I am going to get sodium phenoxide as an intermediate. Sodium phenoxide NaOH is given, so C6H5ONa. I can write this as minus and plus. So this is, the name is sodium phenoxide, and I can again undergo acidification, H plus or HCl I can directly write, and then I will get, so let me write HCl over here such that you can remember. I'll get phenol. Why such high temperature? Why such high pressure? The reason is haloarenes are less susceptible to nucleophilic substitution than alkyl halides. So this is the first method of preparation. Second method of preparation is from benzene. Or rather I can say from benzene sulfonic acid. So from benzene what will I do? I'll convert it to benzene sulfonic acid. Benzene, when treated with oleum, we get benzene sulfonic acid, and that is SO3H group attached to a benzene ring. The name is benzene sulfonic acid. So this is the name, benzene sulfonic acid. Now from benzene sulfonic acid, it is first converted to sodium phenoxide on heating with molten sodium hydroxide and then acidification. So I can write NaOH and comma heat. Number 2, I can do acidification. So 2 steps here I am writing together and I will get phenol. So this thing which I am doing stepwise, point number 1 and point number 2, both I am showing you. This can be done in a flowchart manner. So do follow flowcharts, do make concept maps for your own better understanding. Now next I will say, I can say from benzene diazonium chloride or I can say from aniline. So let me say from aniline, or I can say from nitrobenzene, because I want to teach you another step extra over here. From nitrobenzene. Why nitrobenzene? Because nitrobenzene can be converted to aniline. You know what? That I can start the reaction with benzene as well. I can convert benzene to nitrobenzene. Here I have seen conversion of benzene to benzene sulfonic acid. But if I start with nitrobenzene, I can even start with benzene. See, benzene can be converted to nitrobenzene by nitration. So I can give concentrated HNO3 in presence of concentrated H2SO4, and the reaction is nitration in order to get nitrobenzene. So from nitrobenzene again I can obtain aniline by reduction Sn plus HCl or Fe plus HCl. This is known as reduction. Why? Because reduction is taking place. Nitrobenzene gets reduced to aniline. The structure of aniline is C6H5NH2. So this is known as aniline. Now aniline can undergo diazotization reaction in presence of aqueous NaNO2 plus dilute HCl 0 to 5 degrees Celsius. 0 to 5 degrees Celsius. The name of the reaction is diazotization reaction. Now this will form benzene diazonium chloride N2 plus Cl minus. This is benzene diazonium chloride, a resonance stabilized intermediate. From benzene diazonium chloride, I can obtain phenol just by giving warm water. You just give warm water and you will get phenol. See, when you are preparing this, you need not know the side product. Need not write the side product, but you should know the side product. So, N2 plus HCl are the side products. So, this is how the reaction is taking place. Just have a look completely. It is like this. You can obtain phenol from aniline by diazotization followed by warm water. You can obtain aniline from nitrobenzene by the method of reduction using SnHCl or FeHCl. You can obtain nitrobenzene from benzene by the method of nitration. Now, commercially there is a method of obtaining, that means large quantities of phenol can be obtained from cumene. This is from cumene. Now I hope all of you or many of you know that the name phenol in the market, it is known as carbolic acid. And have you heard carbolic acid at home, where maybe your parents use it during the monsoons to keep your place safe from snakes? So ये जो कार्बोलिक एसिड मार्केट में मिलता है सांप को भगाने के लिए, वो क्या है? वो एक्चुअली फेनॉल है. इट्स वेरी वेरी corrosive. Phenol is very corrosive and very much acidic in nature. So you can obtain phenol from cumene. You know what is cumene? Cumene is isopropyl benzene. Isopropyl benzene. So from this structure, let me make the structure of cumene. Benzene, where I am giving the isopropyl group. This is your isopropyl benzene, which is known in the market by the name cumene. Now, cumene market in the sense for the large scale. Now, cumene is undergoing oxidation. In presence of oxygen, cumene forms cumene hydroperoxide. So, you are seeing this carbon-hydrogen bond here. This carbon-hydrogen bond here. This bond will have a peroxide linkage with it. So you get this type of structure, cumene hydroperoxide. CH3 remains as it is. Again, this part remains as it is. And the CH bond has this peroxo linkage. So the name is cumene hydroperoxide. ओके अब तो आपको मिल गया क्यूमीन हाइड्रोपेरोक्साइड, लेकिन आपको फेनॉल तो नहीं मिला. तो करना क्या है, ये जो क्यूमीन हाइड्रोपेरोक्साइड मिला, it is converted to phenol and you get a side product which is acetone by treating it with dilute acid. So H plus H2O, H plus along with H2O, dilute acid. So you will get phenol. So this is the structure again of phenol. Side product is what? Side product is acetone. So imagine the bond breaking here and the bond breaking here. What comes out is OH attaching to the benzene ring. And see, this is your acetone part. So plus CH3, C double bonded O, CH3. This part. It comes from this part. Just I am highlighting. Let us see this part. So it comes from this part. You get a stable side product, that is acetone. The name is acetone. Okay, this is how you can obtain phenol from cumene. In large quantities you will get phenol. So remember that obtaining phenol from cumene is actually used for commercial purposes because of the good yield. Now, we can see in-text question which is given in your book. When you open the book, you will see it is NCERT in-text question. NCERT in-text question number 4. Show how the following alcohols can be prepared by the reaction of a suitable Grignard on methanol. What is methanol? Methanol is H, C double bonded OH. This is your methanol. So alcohol is given. So do you remember that when we were using Grignard, so first it was RMGX and second it was HOH, and then we got 1 degree alcohol. So how did we write 1 degree alcohol? RCH2OH. This was your 1 degree alcohol or primary alcohol. Now if I say that for the primary alcohol, this part is fixed, CH2OH, and R is coming from your Grignard reagent. So if I know the final structure of the alcohol, and if I know in the final structure what is the R part, can't I find out the Grignard by adding MgX to it? Yes, it's that easy. So let us try out. It is said that the first alcohol is CH3, CH, CH3 and a CH2OH. Just recall what I said, or you can just go back to listen to what I have said. In this structure, I said that CH2OH को अगर छोड़ दे तो बाकी जो पार्ट बचा ये है आपका R, ये है आपका R. तो what is the R part here? Just a minute. What is the R part here? R part is CH, CH3 and a CH3 here. Just observe minutely. It is the same thing which I have written. This is your R part. So to this R part, if I have to give MgX, then it will become your Grignard reagent. Suitable Grignard reagent you have to choose. So RMgX will be what? CH3, CH3 बन गया आपका R, साथ में MgX, X के जगह पे Br चूज करो. दिस इज योर सुटेबल ग्रिग्नाट. तो है ना इजी. एक बार अगर समझ में आ जाता है तो ये बिल्कुल इजी है. तो इसके बाद second part says this is your cyclohexane ring. इसके साथ CH2OH. फिर से वही फंडा जो मैंने बताया, CH2OH को अलग करो और जो बचा वो क्या है, आपका R है. तो R is this thing ना, cyclohexane, उसके साथ ये, तो ये किसी के साथ अटैच्ड है. दिस इज योर R part. And then suitable grignard RMGX should be your cyclohexane ring, साथ में MGX या MGBR. So it is easy. I will not at all believe if you say no, ma'am. It is. Just follow the video. I think it will be helping you. So next, go to question number 5. Write structures of the products of the following reaction. That is the question from your NCERT. So I am writing the question also. Just see CH3CH double bonded CH2, and they have given H2O H plus. Acidic condition, hydration. We have already done. It follows what? Markovnikov manner of addition of HOH. So this carbon is having less number of hydrogen. तो यहाँ पे add होगा OH और यहाँ पे add होगा H to give you the major product. अगर structure of products बताया गया है तो आपको major और minor दोनों दिखाना है. I am showing you the major product. आप minor product खुद से बनाइए. ये OH है, यहाँ पे CH3 है, ये है आपका major product. तो minor क्या होगा? ऑपोजिट होगा. जहां पे OH है वहां पे H, और जहां पे H है वहां पे OH. तो फिर next says this is a compound double bonded O, CH2 C double bonded O, OCH3. इसमें आपका NaBH4. तो याद कीजिए NaBH4 कब लगा था? NaBH4, LiAlH4, they were very strong reducing agents. तो वो strong reducing agent है. लेकिन ये क्या करता है? NaBH4 को आप एस्टर को रिड्यूस करने के लिए ना यूज नहीं करेंगे. और ये रहा आपका एस्टर लिंकेज जो NaBH4 से रिड्यूस नहीं होगा. तो रिड्यूस होगा तो कौन सा होगा? डबल बॉन्डेड O. यू हैव सीन दैट इट इज अ कीटोन लिंकेज. देखिए उसमें हाइड्रोजन है नहीं. कार्बन का 1 2 3 4 वैलेंसी है, जिसमें हाइड्रोजन तो है ही नहीं. तो OH आ जाएगा, यहाँ पे रिडक्शन है, एंड बाकी सब सेम ही रहेगा. CH2 C डबल बॉन्डेड O, OCH3. ये रहा आपका प्रोडक्ट. इसके बाद जो थर्ड है NaBH4 फिर से है. तो आपको NaBH4 का एप्लीकेशन तो NCERT सिखा के ही रखेंगे. तो इसीलिए आप देखिए CH2 CH और यहाँ पे CH3 and you are seeing CHO and then it is given NaBH4. एक चीज ध्यान दीजिए कि ये तो था आपका कीटोन लिंकेज ना, ये लिंकेज आपका कीटोन था. कीटोन से जो अल्कोहल आपको मिला, ये कौन सा डिग्री मिला? ये एक कार्बन दूसरा कार्बन, तो आपको मिला ना 2 डिग्री अल्कोहल. थोड़ी देर पहले ही आपने देखा इसको. तो दिस इज योर एल्डिहाइड. एल्डिहाइड क्या करेगा? NaBH4 है, रिड्यूसिंग एजेंट है, तो ये रिड्यूस होके क्या बनाएगा? अल्कोहल ही तो बनाएगा. सो CH3 CH2 CH CH3 एंड ये रहा आपका अल्कोहल CH2OH. इस कार्बन को मार्क कीजिए जिसमें OH है. इसके साथ कितने कार्बन डायरेक्टली अटैच्ड है? देखिए एक ही है. तो ये बना आपका 1 डिग्री अल्कोहल. और वही तो बताया गया था कि अगर आप एल्डिहाइड लेंगे तो आपका क्या बनेगा? 1 डिग्री अल्कोहल बनेगा. बाय रिडक्शन। और अगर आप कीटोन लेंगे तो आपका 2 डिग्री अल्कोहल बनेगा बाय रिडक्शन। तो आई होप आपको समझ में आया है, एप्लीकेशन भी आपको समझ में आ गया होगा। तो ऑल द बेस्ट, revise the concepts properly, and then I will be going to your physical properties.